Hello, this is Mr. Rollison at Cornerstone Charter Academy. This is the 2020-2021 school year, our honors physics class. This is a video walkthrough for assignment 11.3. Just a quick couple of problems in the textbook. So, of course, there's the assignment. You got to go to the textbook. And the textbook looks like this, by the way. If you are trying to get around in the textbook, you can see the thing at the bottom there where I'm typing right now. You can just enter whatever page number you want to go to there, and it will take you there, because it'll take you a long time to flip through the whole thing. Oh, there's kinematics. You don't want to go back there, do you? 326, I think, was the page, was it? Yeah, 320 is page 326, number 1 and 2. So here we go. Let's make it bigger so we can see it. There's 326. All right, so number 1, when you turn on the hot water to wash dishes, the pipes heat up. How much thermal energy is absorbed by a copper pipe with a mass of 2.3 kilograms when the temperature is raised from 20 to 80 degrees C? All right, so first thing first, let's see. We need our little formula, right? So let's, why is that? Huh. I am confused by something. I don't know. Something's not working. Apologize for a moment because something's not quite working with this thing here. Okay, so the eraser's working. And, oh, there's the point. Okay. I've got something, maybe you can see it. I don't know. There's a bar of text over my controls. So I need my pointer. So what we need to do is go back here, and what we're looking for, we need a couple things. We're going to need the specific heat of copper. Just to refresh your memory, specific heat, it's right there. Specific heat is the amount of energy it takes to raise the temperature of a particular material, 1 kilogram of that material, 1 degree Kelvin. So it's in joules per kilogram Kelvin. Now, that is in kilograms, but a lot of times you're going to find it in a cubic centimeter of, or a gram, excuse me. You're going to find the specific heat. Like if you go look up on the internet, okay, let's just say we're going to need the specific heat of copper, and that's 385. It's right there. That's copper, 385. So if that's that's the amount of joules of energy it takes to heat 1 kilogram of copper, 1 degree. If you look on the internet, there's a good chance you're going to find it in grams per degree Kelvin instead of kilogram. Joules per gram degree Kelvin instead of joules per kilogram. So if you look on the internet and you try to verify that, you're going to find it says 0.385 instead. So don't let that confuse you. That's just grams to kilograms. And it should be in kilograms because kilograms is a base unit in the metric system. But okay, so that's what we needed to know there. And then we're going to have to go back 1 page further, I think, to get that equation. No, maybe 1 page forward. Maybe it's up here. Here, maybe it's on the next page already. Well, I know it's in the next page because that's where the exam. Oh, there it is. Okay, the heat. So Q, heat, that's the amount of energy in joules. And the formula that we're looking for to finish our problems is this one right here. Q equals M. M is the mass. That's the mass. C, that's the specific heat. That's the one we just looked up, which we're going to have to look up again because I can't remember what the specific heat of copper is already. And delta T right there, that's the change in temperature. So that is just this little bit right there. That's the final temperature minus the initial temperature. That just gives you the change in temperature, right? So we will erase all that. We'll go back and, was it 384? Oops, too far. 380, was it 384? A specific heat of copper? 385. I was very, very close. Okay, here we go. All right, so what's our first question here? The first question is, okay, I'm going to write down the specific C of copper equals 385. That's joules per kilogram per degree Kelvin. So remember, that'll be 0.385 because on the internet it might say per grams instead of kilograms. Okay, so you turn on the hot water wash dishes. The water pipe heats the pipes up. How much thermal energy Q is absorbed by the water pipe with a mass of 2.3 kilograms when its temperature is raised from 20 to 80 degrees Celsius. So that's pretty straightforward to set up. Q, that's the heat, that's what we're trying to find out, is the mass. And they give us, it's 2.3 kilograms. You always want to make sure you're using the same units. And our specific heat is in joules per kilogram per degree, so that's fine. So we got 2.3, that's the mass. Specific heat of copper is 385 joules per kilogram per degree Kelvin. And we want to raise it from 80, from 20 to 80. So our final temperature is 80 minus our initial temperature of 20. So that, of course, is going to be 60. And then we just have to go in my desk because I'm not prepared well enough for this. And the answer is going to be 2.3 times 385 times 60. And that means it's going to take 53,130 joules. Okay? Or if you want to go all sciencey, you can say 5.313 times 10 to the fourth, because the implied decimal is right there, right? And you go 1, 2, 3, 4, but then you have to multiply it by 10 to the fourth. So there's the answer to the first one. Now we'll do the second one. Oh, that little annoying bar left. I'm so happy about that. Oh, I realized I have music on too. Okay. Electrical power companies sell electrical energy by the kilowatt hour, where 1 kilowatt hour equals 3.6 times 10 to the 6 joules. Suppose it costs 15 cents per kilowatt hour to run your electric water heater. How much does it cost to heat up 75 kilograms of water from 15 to 43 degrees C? Okay, so first we're going to calculate the energy that it takes to heat that water, right? That's going to be the energy is going to equal the mass times the specific heat times the change in temperature, right? So it's going to equal the mass, how much water? 75 kilograms of water times the specific heat of water, which I happen to know is 4180. If it's not, it's 4181, and I'll just go check. I should model better than that. Water, 4180. I'm right. Okay. So 4180 times the change in temperature, which is going to be the final temperature, minus the initial temperature. And now we do it. So let's see. Clear. 3 minus 15. That's 28. There's a 28 degree change in temperature times 4180 times 75. So that's a lot. It's just a plain old lot right there. That's 8,778. Because water has a very high specific heat. It takes a lot of energy to change the temperature of water. Isn't that interesting? Which is a good thing for those of us who live near water because it keeps our weather temperate. So there it is in all its glory, but that's not the answer, right? Because it costs 15 cents per kilowatt hour to run your electric water heater. That's how much energy it will take. And a kilowatt hour is 3.6 kilowatt hour equals 3.6 times 10 to the 6th, which, if you don't like scientific notation, it's going to be 3, 1, 2, 3, 4, 0.456. So just to walk you through that, the decimal place point was right there, right? But it's times 10 to the 6. So we go 1, 2, 3, 4, 5, 6. So that's where we are now. So all you got to do is take the amount of energy used, divide it by the cost per kilowatt hour, based on the fact that a kilowatt hour is 3,600,000 joules. And you'll get the answer. And you can do it in scientific notation, or if you just like punching zeros on your calculator, you can do it the old-fashioned way. I shouldn't say old-fashioned, but so that's how much joules per kilowatt hour. So it's going to take 2.44 kilowatt hours, right? Because that's the amount of joules. That's joules per kilowatt hour. So that if we take the first divided by the second, we find out it takes 2.44 kilowatt hours, and then we'll multiply that times what, 15 cents? Uh, 2.4 times 15. So that equals 0.3, it's 37 cents. So, next time you take a bath, leave your parents 2 quarters on the side of the tub and say you just wanted to, take care of business for your bathtub. I think power right now in Florida actually goes for about 12 cents a kilowatt hour. So, maybe leave them a quarter. Anyway, that's it. That's the whole assignment. I hope you turn it in. Bye-bye.